finished up to the spherical spheres. We were doing Gauss law. In Gauss law, we have finished the line charge. We have finished all type of spheres. After spheres, the next topic is electric field due to a plate and a sheet. Electric field due to infinite plane sheet. So if you have an infinite plane sheet, sheet is two-dimensional. Sheet will have only surface charge density. So the charge density of the sheet is plus sigma. If you want to calculate electric field due to the sheet, we are not doing derivation. Derivation will not help in any numericals. So due to the sheet, the direction of field is away from the sheet. If this is positive, it's away from the sheet. If it is positive, it's away from the sheet. Also, the field is perpendicular to the sheet. This field is perpendicular to the sheet. So if your sheet is along YZ plane, then your electric field is along x-axis. And the expression of field is sigma by 2 epsilon. This is the field. So there are certain types of problems on this concept. That's you have two sheets. One have charge density plus sigma 1. Then you have another sheet. This have charge density minus sigma 2. And you're supposed to calculate field in three regions. Region 1, region 2, region 3. So in this region, we'll apply the superposition principle. Both the sheets will generate fields here. So for the first sheet, the direction of field is away from the charge, that is E1. For the second sheet, the direction is towards the charge, that's E2. In the second region, due to the first sheet, it's away from the charge, it's E1. Due to the second sheet, it's towards the charge, which is E2. So if you calculate net field in region 1, this is E1. If I take E1, the magnitude of E1 is sigma 1 by 2 epsilon naught, and we take direction. It's along negative x-axis. Negative x-axis, it's minus of I cap. Similarly, it's E2, which is sigma 2 by 2 epsilon naught, which is I cap. So this is field in the region 1. Similarly, if you want to calculate field in region 2, for the first sheet, it's sigma 1 by 2 epsilon naught. Direction is along positive x-axis, which is I cap. Similarly, for the second sheet, it's sigma 2 by 2 epsilon positive x-axis. This is I cap also. So this is how we calculate electric field for a sheet. After sheet, you have one more thing. This was not in NCERT. Electric field due to infinite plate. Due to infinite plate. This was not in NCERT. So the difference infinite conducting plate. So the difference between sheet and plate is in sheet there is one single surface, but in plate it's double surface. So if you take plate, this have double surface. Plate have double surface. One surface here and one surface here. So if you give charge, there also surface charge density is plus sigma. Here also surface charge density is plus sigma. If you want to calculate field here, so both the surfaces will generate field here. So if you want to calculate field here, due to positive charge, the direction of field is away from the charge. Similarly, due to another positive charge, the direction of field is again away from the charge. So if you want to get the value of field, both the fields are in same direction. So it's sigma by 2 epsilon naught plus sigma by 2 epsilon naught. It comes out to be sigma by epsilon naught. So for a plate, here also the direction of field is away from the charge and the value of field is sigma by epsilon naught. That is the difference between sheet and plate. So if you have a sheet, infinitely plane sheet, the electric field is sigma by 2 epsilon naught. But instead of sheet, if you have a plate, conducting plate, Then conducting plate have double surfaces. So field is sigma by epsilon naught here. And similarly, sigma by epsilon naught here. So there are few types of questions which are usually asked on plate. The one question is, if you have a plate and if you want to calculate field inside the plate, Upasna, what should be the value of electric field inside the plate? Mira, what should be the value of electric field inside the plate? Upasna, you were saying
So
something.
is it zero because it's conductor?
Yeah, or you can easily calculate also. No, it should be zero. See, this is first plate. So direction of field is away from the charge E1. This is second plate. Sheet. Direction of field is away from the charge E2. Both the fields have same magnitude and they are acting in opposite direction. So field inside is zero. Now we'll come to the type of questions on it. So you have a plate and you give some charge Q over the plate. You have to decide how the charge will distribute on the both the sides. So if you're giving charge Q, then there are various type of division. The charge gets equally divided here Q by 2, here Q by 2, or it's also possible that here you get some charge like Q by 4. On another side, you have 3Q by 4. So you have to decide the distribution of charge. For this, what you can do is you don't know what is the value of charge on this sheet and what is the value of charge in this sheet. So you will start with X. Here, it's X. Here, the value is Q minus X. So at one side, the charge is X, another it's Q minus X. If you want to get the value of charge density, it's nothing but charge upon area. It's nothing but charge upon area. This is phase 1. This is phase 2. You need field inside the conducting plate. Here it's E1. Here it's E2. So inside, you know that net field inside is 0. So E1 minus E2 will be equal to 0. Or you can write that E1 will be equal to E2. Or you can simply write X by A is Q minus X by A. So field is sigma by epsilon naught. So X by A or by epsilon naught. This will get cancelled out here. So you have X is Q minus X. Or you can write, take this Q to the left hand side. You have 2X equal to Q. And you can write that your X is Q by 2. Is it clear? Both?
Yes.
Yes.
Yes, sir.
So just keep this thing in mind. Sheet and plates are two different things. Whenever you have plate, it's a conducting plate. Non-conducting plate is a very different system. So difference is, for sheet, the field is sigma by 2 epsilon naught, but for plate, it's sigma by 2 epsilon naught. Just note it down fast, then we'll do one more numerical on plate. Just keep telling me when you have written. I will just scroll it down.
Done, sir.
Done, sir. Done, sir.
Sure.
Done, sir.
चलिए.
Done, sir.
So we'll solve this question together. So in this question, two sheets are given, two plates are given, sorry, two identical metal plates, each having surface area and having charge Q1 and Q2. So for this metal plate, charge Q1 is given, to this metal plate, charge Q2 is given. You have to calculate charge on each face. Now, one wrong answer is you can say that if you go to the previous problem, in the previous problem, charge gets equally divided on both the faces. You can say, okay, it will be Q1 by 2, Q1 by 2, Q2 by 2, Q2 by 2. But along with the division of Q1, there is one more source of charge, and that is induction also. Due to induction, some charge can go from 2 to 3 or some can go from 3 to 2. So due to induction, the charge will not get equally divided because you have two different plates. Here you had a single plate. There is no chances of induction. That's why we just divide the charge into two parts. But here this is induction. So charge cannot get equally divided. So we will start with, this is first plate. Let's say some charge is here, it's X. So here your charge will be Q1 minus X. Then take another plate. Total charge that was given to the plate is Q1. So if one phase this is X, then another it will be Xq1 minus X. Due to induction, this is plate 1, this is plate 2. Here the charge will be minus of X. And the charge on the next phase will be Q2 minus of X. So this will be Q2 plus X. Or instead of 1 and 2, let's write the name of the phases. So there are four phases: phase 1, phase 2, phase 3, phase 4. If you have charge, then you have charge density. Charge density is nothing, charge divided by area. So you have charge density or all four phases. You're supposed to calculate the electric field, the value of X. So to get the value of X, you need an equation because there is one single variable which is X. So one single equation, you can say that electric field inside this conductor is 0. You can take point here or here, it's equivalent. You can take point anywhere. So I'm taking here, I'm saying electric field here is 0. So here electric field is generated by the first phase. So on the first phase, charge is positive. So direction of field is away from the charge, that's E1. On the second phase also the charge is positive. The direction of field is away from the charge, so that's E2. On the third phase, the charge is negative. So the direction of field is towards the charge, that is E3. On the phase 4, charge is positive. The direction of field is away from the charge, that's E4. You know that net field inside the conductor is 0. This is 0. 0 is possible only if on the left hand side, field on the left hand side and field on the right hand side are equal. So we can say that E2 plus E4 is equal to E1 plus E3. E2 is X by A epsilon naught. E4 is Q2 plus X by A epsilon naught. E1 is Q1 minus X by A epsilon naught. E3 is X by A epsilon naught. Oh, sorry, not it's sigma by, not sigma by epsilon naught, sigma by 2 epsilon naught. So I should write 2 here. Yeah, is it clear up to this step? After this step, this simple calculation, this simple math algebra. Upasna and Veera, is it clear up to this step?
Yes, sir. Clear.
Yes, sir.
Now this 2 epsilon naught, 2 epsilon naught, 2 epsilon naught, 2 epsilon naught gets cancelled out. So you have 1x here, 1x here, 2x. This minus x and x will cancel out each other. So we have 2x here. It's q1, q2 will go to the right hand side. It will be q1 minus q2. So you can write that your x is q1 minus q2 by 2. So when you have x, that means you have charge on all four faces. On the face 1, charge on face 1. On face 1, it's q1 minus x. So it's q1 minus q1 minus q2 by 2. So this will be 2q1 minus q1 plus q2. So that is q1 plus q2 divided by 2. On phase 2, the charge was equal to x. So it's just q1 minus q2 by 2. This is phase 2. Huh? On phase 2, the charge is x only. On phase 3, charge is minus of x. Charge on phase 3, it's minus of x. So it's minus of q1 minus q2 divided by 2. On phase 4, charge is q2 plus x. So q2 plus x is q2 plus q1 minus q2 by 2. 2q2 minus q1 is q1 plus q2 divided by 2. So these are the charges on the four faces. So if instead of a one plate, you have two plates, then you have to do division of charge, and then using the fact that electric field inside a conductor is 0, you can calculate charge on the individual states, individual phases. Note it down. So that was about Gauss law. After Gauss law, we'll move on to potential. Tell me once you have written. Huh?
Done, sir.
Okay. So that was about electric field. The next topic is electric potential. Electric potential. Electric field was related to work done, and electric field was related to force, and electric potential is related to work done and then to potential energy. So we'll start. Electric potential is in two parts. One is the general discussion on electric potential. In general discussion, you will learn how to calculate work done if field and potential is given. Then we'll calculate how to calculate potential from field and how to calculate field from potential. Then we'll come to potential of individual charges. The way we calculate electric field due to individual charges. We calculate electric field due to a point charge, sphere, line charge, sheet, and all. Similarly, we'll calculate potential due to them. But before starting this electric potential, let's discuss what is potential basically. So, in a very language of a layman, what is potential? Potential is nothing but it's a scalar quantity, it's a scalar function which defines electrical properties of a point charge. So, it's a quantity which define electric properties around a charge. Electric properties around a charge in scalar form. So if you have a charge, there is some electrical properties around the charge. Means there is a certain region in which a charge can attract or repel any other charge. That the electrical property of that region in vector form it's given by electric field. In scalar form it's given by electric potential. This is connected to work done. So if you want to calculate electric potential difference, or let's start with work done first. So work done by field. Work done by field. So we'll keep this discussion very, very general. It's valid for all types of charge configuration, whether it's a point charge or a sphere or a line charge or sheets. This discussion is absolutely independent for a particular type of charge distribution. So work done by a field. So you have a field. This is some electric field. And in this field, we take 2 points. One is point A, another is point B. And you have a charge Q. You're supposed to take this charge from point B to point A. So to take this charge from B to A, you have to do some work done. So we'll calculate first work done by external force, and then we will connect that work done by external force to work done by electric field. So work done by external force in carrying charge from B to A, it's minus of Q, the charge that you are taking, integral of E dot dr, and you will integrate it from B to A. This is the simple work done. But if your electric field is uniform, if E is uniform, if electric field is uniform, then this calculation gets very easy. In that case, work done by external force from B to A is nothing but it's minus of Q. You can take this E outside, the integral of dr will be r, and you can write this as it's minus of Q E dot RA minus RB. It's RA, or you will get confused. Usually you people remember A to B. So let's call this point as A and call this point as B. So let's calculate work done from A to B, not from B to A. Otherwise you can get confused in it. Yeah. So we need work done from A to B. So we will integrate it from A to B. So E is uniform. You can take it outside the integral sign. When you integrate dr, it will be RB minus R, and upper limit minus lower limit. So that's E dot RB minus Ra. This is the work done by external force. So you will use this expression when your field is non-uniform. This is for a non-uniform field. But if your field is uniform, then instead of integral, use directly dot product. That's work done by field. If you need work done by electric field, if you need work done by electric field, work done by electric field. To calculate work done by electric field, just take negative of work done by external force. That's the relation. So always we will calculate work done by external force. So for field, we'll just take negative of it. That's work done by electric field. After work done by field, we will connect potential difference with work done. Potential difference. So for potential difference, what we will do, let's say you have a charge. This could be of any type of charge, point charge, line charge, volume charge distribution, anything. And then you have 2 points. One is point B and another is point A. At point A, potential is VA. At B, potential is VB. You are supposed to calculate VB minus VA. So to calculate VB minus VA, what you will do, you will take a test charge. You will take this test charge from A to B and you will calculate work done. Work done by external force in carrying this test charge from A to B. And then you will divide this work done by the test charge. This will give potential at B minus potential at A. Work done we have already calculated here. So from there, you can relate this potential difference with the electric field also. So you can write this as minus of its A to B integral of E dot dr. So what I did here, I just substitute this value, this work done from A to B minus QE dot dr here. Similarly, if your field is uniform, then again I will divide this work done by Q. So we'll be left with just minus of E dot RB minus RA. That's what. So what kind of quantity is potential? The scalar quantity. Its SI unit is volt. It's joule per coulomb, and that joule per coulomb is known as volt. This is general discussion. So if you have field, is a non-uniform field, then you will integrate the field and you get potential difference. But if you have a uniform field, then just simply take E dot RB minus RA and you will get the potential difference. Now, after potential difference, you can also calculate potential. So the difference between potential difference and potential is, in potential difference, the initial point, which is also known as the reference point, is at a finite distance. But when you calculate potential, then your reference point is at infinity. You have to bring your test charge from infinity to a point B. If you want to calculate potential at B, then you will bring your charge from infinity to B. If you want to calculate potential at A, then you will bring your charge from infinity to A. So potential at B is work done in carrying your charge from infinity to B by external force divided by the magnitude of test charge. That can be written as minus integral of infinity to B E dot dr. And remember, if your field is uniform, then potential does not exist. For uniform field, potential difference do exist, but potential does not exist. So that I can write here. For uniform field, for uniform electric field, potential does not exist. Potential does not exist. Uniform field means field which is independent of position, like the field of an infinite plane sheet that was uniform. Field of an infinite plate that was uniform, that was independent of R, that was independent of X. So if you have that type of field, potential does not exist. Potential difference do exist, but potential does not exist. The problem is, if this is uniform, you can take this E outside. When you integrate this dr, you will get infinity. You will get r, then you substitute the limit up to infinity. You will get infinity. Any physical quantity cannot have the value infinity. That's why if you have a uniform field, potential does not exist. That's a conceptual type question. So up to here, what we do, we did like if you have field, then how to calculate potential. If you have field, then how to calculate work done. Now we will go just the opposite side. Like if you have potential, then how to calculate field. If you have potential, then how to calculate work done. Is it clear up to here?
Yes, sir.
Okay. Note it down, the whole discussion. Then we'll do work done in terms of potential. Then we'll do field in terms of potential. And then we'll come to the numerical from the PYQs. And keep telling me when you have written.
Done, sir.
It's okay. Did you finish optics with Amna?
No, sir. Lenses left.
Lenses. Your exam is on 7th, no? 6th or 7th?
I have it on 7th.
You have on 7th and Mira, you have on 6th.
Eh,
It's okay.
No, sir.
I believe there is only one test center in Riyadh, na?
Yes, sir. Only one.
So Mira, I got confused. You two have on 7th or you have on 6th?
Sir, I have on 8th on
You have
Tuesday.
on 8th, okay.
Uh,
Sure. And you have on 7th of us, huh?
Yes, sir.
So we have up to 6th. We have to finish this potential, capacitance, and then modern physics. Let's do it fast.
Done, sir.
It's okay.
Done, sir.
See, the 50% of paper is from class 12th. Huh? Just revise everything. Did you get the books, all three PYQs?
Yes, sir.
Yes.
Try to solve at least last 5 years or 4 years questions from that book. From the complete paper, you just have to solve 25 to 30 questions. That's it. You don't have to solve all 75 questions. 25 to 30, including all three subjects, and you'll get a decent percentile. From which state are you people? Upasna, you're from which state in India?
Kerala, sir. Kerala.
Kerala. Mira?
Kerala, sir.
Kerala. So in Kerala, you have NIT or Trivandrum. Cut off.
Done, sir.
It's NIT Calicut, na?
Yes, sir.
So if you can get 25 questions correct out of 75, you will get admission in NIT Calicut. Written? Can I scroll down?
Yes, sir.
Yes, sir.
So 10 physics, 10 chemistry, 5 from maths. Maths is usually very tough in JEE. And remember one thing, avoid any guesswork in your exam. That will just contribute to negative mark, nothing. Avoid negative marking. So okay. So that was about potential and potential difference. Now let's see how to calculate work done if potential is given and how to get field if potential is given. So let's move on to work done again, but in terms of potential. So you have 2 points, a point A and a point B. You have the potential at A is VA and potential at B is VB. There is some charge configuration which is producing this potential. We are not interested into that charge configuration. We are not interested into the source which is producing VA and VB potential. Some source which is producing VA here and VB here. Then you take a charge Q, you bring this charge Q from A to B. So you want to calculate work done by external force in carrying charge Q from A to B, and that work done is charge Q, potential at B minus potential at A. So this is work. So work done in carrying a charge from A to B is charge multiplied by potential at B minus potential at A. So this is work done in terms of potential. This is easier method to calculate potential, calculate work done, and this is a bit tricky. If you have field, that means a lengthy calculation. If you have potential and you want to calculate work done, it's a comparative easier calculation. Now, what if you have potential and you're supposed to calculate electric field? So electric field in terms of potential. Electric field in terms of potential. So your electric field is equal to gradient of potential. It's minus of dV over dr. It's gradient. What does gradient means? Gradient means change with respect to position. So you have 2 points, one A, another B. They have a separation dr, and the potential difference between these 2 points is dV. So the electric field between these 2 points is dV by dr, gradient of potential. And this negative sign gives the direction of field. Negative sign shows, negative sign says that potential decreases in the direction of field. Potential decreases in direction of field. So potential will decrease in the direction of field. Means if you have this field and we take 2 points, one is point A and another is point B, and this is the direction of field. Now if I ask you to compare the potential at A and B, when you go in the direction of field, potential decreases. So you can say that potential at A is higher and potential at B is comparatively lower. So at A it's high potential, B is low potential. Field is always from high to low potential. This type of derivative is known as total derivative. So there's one more thing. If you are differentiating V with respect to R, then you are not getting E. You are getting a component of E which is along R. This is component of E. This is component of E along R. Similarly, if you want to calculate Ex, component of field along x-axis, then it's minus of dV over dx. Or you can say that if potential change along x-axis, then you will get x component of field. If potential change along y-axis, then you get y component of field. If potential change along z-axis, then you will get z component of field. Whenever potential change, you have field. But what if your potential changes in all direction? Like you have a potential which is a function of x, y, and z all. Then you will have x component of field, y component of field, and z component of field. So you can say the x component of field is minus of del v over del x. Similarly, y component of field is minus of del v over del I. Similarly, z component of field is minus of del v over del z. This del v means it's partial derivative. It's not total derivative, this is partial derivative. So how to perform partial derivative? If you have x, y, z all and you are differentiating with respect to x, then consider y and z as constant. That's it. That's partial derivative. There's one more thing. If your potential is constant, see, field comes due to change in potential. If potential is constant, then your field is zero. If in a region potential is constant, then field is zero. But if in a region delta V is constant, then you can write your field as minus of delta V over delta R. Understand the difference in two expressions. Here potential is constant, but here change in potential is constant. If potential is changing, you'll definitely get field. Now this delta R is again tricky. What is delta R? Delta R is perpendicular distance between points in direction of field. In direction of field. All these things were in class 12 board syllabus also, na? In the direction of field, that's it. So that means if you have field, this is your field, and I take 2 points. One is point A, another is point B, and you want to calculate potential difference between A and B, then what you will do, you need perpendicular distance between A and B. So this is A, this is B, this is perpendicular distance between A and B. You need perpendicular distance in the direction of field. You can also take this is also the perpendicular distance. But this is not along the field, this is perpendicular to the field. You need perpendicular distance which is along the field. Along the field, you need perpendicular distance. So if your delta V is constant, then E is minus of delta V delta R, or you can write that your delta V is minus of E delta R. There's one more interesting thing. If delta V is constant, then your E is uniform. It's a uniform field. So that is the general discussion which involves field, which involves potential, and which involves work done. Well, let's see what type of questions one can get in PYQs from these topics. Note it down. Haji, written?
Yeah. Done, sir.
Done. Okay.
Done, sir. Done, sir.
Okay. Yes, written.
Yes, sir.
Yes, sir.
So, okay. And write this about delta R also. Perpendicular distance between point in direction of field. Okay, now use this concept and solve this question. Okay, now let's solve this together. So electric field is given, E is given, and you're supposed to calculate V1 minus V2. Field is uniform or non-uniform? Upasana, Mira, is it uniform or non-uniform? Field. See, in the
Uniform.
expression of field, no. You have X, right? X is a variable. So field is non-uniform. If instead of X, you have just A plus B I cap, then you can say it's a uniform field, but it's a non-uniform field. So you have a non-uniform field and you are supposed to calculate potential difference. Just check your notes and tell me which formula you'll be using. You need V1 minus V2 and you have a non-uniform field. Upasana, which formula you will use? Mira?
Minus integral A to B electric
Yeah.
field ER.
Yeah. So your electric field is AX plus B I cap. Now, if your electric field is along I cap, then your dr should also be along I cap. So we'll use dx I cap. If your electric field is along j cap, then we're using dy j cap. If it is along k cap, then we're using dz k cap. And you have to integrate it from v1 minus v2 means you initial point is 2, final is a1, right? We go from initial to final. So if this is your final point, 1, and this is your initial point 2. When you go from 2 to 1, then we write v1 minus v2. Means this is initial and this is final. When we integrate from 2 to 1. We integrate from initial to final and we write potential as final minus initial. So we can write this as minus integral of 2. So point 2 means at if the potential at x equal to 1 is v1 and x equal to minus 5 is v2. So the point at which potential is v2 is your point 2. So your initial limit will be minus 5. Then your final limit will be x 1. And then you have this integral. When you take dot product, you can write this is ax plus b into dx. I'm repeating again how to decide which is initial and which is final. You're supposed to calculate v1 minus v2. Potential difference is always final minus initial. So v1 is final, v2 is initial. And we always integrate from initial to final. So we'll integrate from 2 to 1. So for v2, x is minus 5. So we'll integrate it from minus 5 to 1. So minus is different. Now let's integrate it. If you take a is outside, what is the integral of x?
X square by
1.
2.
X
X square by 2.
square by 2. Limit is minus 5 to 1. Plus b outside, integral of dx, which is x. Limit is minus 5 to 1. So your v1 minus v2 is minus of, it's a by 2. Then if I substitute the limit, it's 1 square minus 5 square. So 1 square minus 25. So that's minus 24. Plus b, this is 1 minus minus 5. So it's 6. 2 outside, 1 square is 1, 5 square is 25, right? And the value of a and b is also given. A is 20 and b is 10. So instead of a, I can write 20, and instead of b, I can write 10, and then this is 6. So you have minus, it's 10 and minus 2, it's minus 240 plus 60. So it's minus of 180, which comes out to be 180 volt. So this is 180 volts, the option. Is it clear, the whole calculation?
Yes.
Yes.
You just have to integrate it. Just note it down, we'll do another type of question. Question in which potential is given and you're supposed to calculate field. Yes, written.
Done, sir. Yes.
Sure.
Yes, sir.
Now read this question. Just note down the question up to here and tell me which relation we'll use here. First decide what is given and what you're supposed to calculate. Yes, Meera, which relation you will be using here?
A is equal to minus dv by dr.
So you will be different. This will be total derivative or partial derivative? check. V is a function of x only, so we'll do total derivative. But if it's a function of x, y, z all, then we'll do partial derivative. So it's minus of dv over dx. So when you differentiate it, it's minus 20. It's divided by x square minus 4. No? Okay. It's minus 20 by x square minus 4. So when you differentiate it, you will write minus 20 will go as it is. This is x square minus 4 to the power minus 2, and due to a negative sign, this gets positive. And then you will integrate x square, differentiate x square also, that will be 2x. So that is your value. Is it clear, this differentiation? It's 20 by x square minus 4. So it's chain rule, x square minus 4 to the power minus 1, it goes to the numerator. And you have to substitute x equal to 4 here. So your field will be 4 micrometer, everything is given in micrometer only. So it's 20. It's 16 minus 4 to the power minus 2. Then you have 2 into 4. So you have 20 into 16 minus 4 is 12. It's 12 into 12 into 8. So this is 4 3s are 12, 4 2s are 8, 4 5s are 20. And then you have 2, and this is 12 also, 2 6 are 12, 5 by 18. Let's check the calculations again. It's 20 by x square minus 4. So minus 20 x square minus 4 minus of x square minus 4 power minus 2, right? Into 2x, 16 minus 4 into 8. So it's 20, 16 minus 4 is 12. 12 square is 12 into 12. It's 8, 4, 2, 4, 3, 2, 6. Yes, 5 by 18 only. Yes, it will be 5 by 18 only. There's some issues in any one of the options. Basically, it repeated both. No, it's not the repeated. It's minus x-axis and plus x-axis. There's some issue with the options. Just note it down. It's 20 by. Yes, is it clear?
Yes, sir.
Okay. In the same question, there's one more possibility. Like instead of one single function, you can get 3x square y cube z to the power 4. Now you will use partial derivative, and you are supposed to calculate field at 0.111. So in partial derivative, what we will do, we will when you're calculating ex, you will differentiate v with respect to x. When you differentiate v with respect to x, then you will consider y and z as constant. So we'll write this as minus of 3 y cube z to the power 4 2x. So this is minus of 6x y cube z to the power 4. Similarly, when you need Ey, this is minus of del v over del y. So your x square and z to the power 4 are constant now. You just have to differentiate with respect to y. So y cube is 3y square. So it will be minus 9 x square y square z to the power 4. Similarly, if you want to calculate Ez, it's minus of del V over del Z. So this is Z to the power 4, it's 4Z cube. So it's minus 12 x square y cube z cube. At 111 means substitute the value of x, y, and z as 111. So this will comes out to be minus of 6 Newton per coulomb. This will comes out to be minus 9 Newton per coulomb. This comes out to be minus 12. So you have to substitute the value only. And you can finally write that your field is Ex I cap. So your Ex is minus 6 I cap minus 9j cap minus 12k cap. That is your field. And if you're supposed to calculate the magnitude of field, then you can use this relation. That's root over 6 square, 9 square, 12 square, and everything. No, no. Let's do one more question on the same concept.
Done, sir.
Okay. Just one more question, same type of concept. Or I can give those questions into homework also. I'll give those questions to homework. Let's move on to the next topic. So this is about the potential relation between electric field and potential. Now we'll come to potential due to different types of charge configuration. The way we calculated field due to different types of charge configuration. The first one is electric potential due to a point charge. Electric potential due to a point charge. So if you have a point charge and you're supposed to calculate potential at some separation R, then potential due to a point charge is Q by 4 pi epsilon naught R if it is a positive point charge. But if it is a negative point charge, then potential at a separation R is minus of Q by 4 pi epsilon naught R. This is for a positive point charge and this is for a negative point charge. Potential is scalar quantity. For positive charge, it's positive. And for negative charge, potential is negative. After point charge, if you have an n point charges. So just like field, calculate potential due to individual charges and then add them up algebraically. You can do one more thing. You can calculate potential due to individual charges and you can add them up vectorically. But if that is true, if you have a vector quantity which is field. But potential scalar, just calculate potential due to individual charge and then just add them up algebraically. This is how we calculate potential due to a system of n point charges. We should do one question over it. Note it down. We'll do one question from PYQs only. Or I'm writing one question. The PYQ I'll give homework. So say you have a square. On each vertex square, you have a charge plus E, plus 2E, minus 2E. Each side of the square is A. This is the center of the square. This is the point O at the center. This is the point, let's say some point A here. This separation is A by 2. You're supposed to calculate potential at O, potential at A, then work done carrying an electron from O to A. Now, if you want to get the value of potential at O, each side of square is A, you need this separation. Upasana, how much is this separation? If each side of the square is A, then how much is this separation?
Root a square plus b square.
A by root 2, right? It's half of the diagonal of the square. Similarly here, this is A by root 2. This is A by root 2. This is A by root 2. You're supposed to calculate potential at O. Then potential at O is K. First charge is E. Separation is A by root 2. Second charge is minus E. Separation is A by root 2. Third charge is plus 2E. Separation is A by root 2. Fourth is minus 2E. Separation is A by root 2. So they gets cancelled out and net potential at the center is 0. Now, when you calculate potential at A, then you need this separation. Mira, how much is this separation? How will you calculate this separation? Here to here. Similarly, you will need
So
this
by
separation.
Pythagoras theorem, root
Pythagoras
of
theorem,
a
right?
square plus.
Yeah, A square and A square by 4. So that will be 5A square by 4. So that will be A by 2 root 5, right? So this is also A by 2 root 5 and this is also A by 2 root 5. So you can say that potential at A is K, which is constant. Then E and separation is A by 2 root 5. So this is E by A by 2 root 5. Then you have minus E by A by 2. Then you have plus 2E. So it's plus 2E by A by 2 root 5. And then you have minus 2E. No, sorry. From 2E, the separation is A by 2. No? So it's A by 2. Then you have minus 2E and separation is A by 2 root 5. So you can take this K E A by 2 as common and you will be left with 1 by root 5 minus 1 plus 2 minus 2 by root 5. So this is potential at A, which is 2KE by A. So minus 1 plus 2 is 1 minus 1 by root 5. This is potential at A. I need work done. Work done in carrying electron from O to A. Work done in carrying electron from O to A. So to carry electron from O to A, its charge of electron formula is this, na? Q potential at A minus potential at O. So here Q is charge of electron, which is minus E. Potential at A is this 2KE by A, 1 minus 1 by root 5, minus potential at O, which is 0. So that's minus of 2KE square by A, 1 minus 1 by root 5. So this question can be repeated. Instead of a square, you can get a hexagon, you can get a semicircle, all types of configuration could be there, but the method is same. Note it down, they'll do sphere. Written?
Yes.
Yes, written.
Yes, sir.
Okay. After point charge, we'll directly jump to sphere. We'll be discussing dipole, line charge, and all, but first with sphere, because if you look at the PYQs, there are major number of questions on sphere. Electric potential, due to sphere. Now you have various options. Sphere could be conducting, or sphere could be non-conducting, hollow. If it is hollow, then it could be conducting or non-conducting, or it could be your solid conducting sphere. We have already discussed this thing in Gauss law. Solid conducting sphere. So this is a sphere. The radius of the sphere is capital R. The charge distributed over the sphere is Q. Due to the sphere, first you have to calculate potential outside the sphere. So when you calculate potential outside the sphere, this is kq by r. For a point charge, for a point outside the sphere will behave like a point charge. For a point on the surface of the sphere, if I take a point on the surface, V surface is kq by capital R. If I take a point inside the sphere, then this is a bit unusual. Inside the sphere, field is 0, but inside the sphere, V inside is exactly same as that was on the surface, and its value is kq by capital R. So potential inside the sphere is equal to potential on the surface of the sphere, which is kq by R. And this is the value at the center also, because center is also inside the sphere. So if you want to plot V versus R graph for a sphere, this is R and this is V. Up to surface, your potential is constant and then it decreases. Using this graph, if you want to predict your electric field versus potential graph, position graph, the region in which potential is constant, your field is zero. So here, your field will be zero. If you look at the graph that we have plotted for in Gauss law, up to the surface, your field was zero, and then it goes as 1 by r. Because the potential is constant and field cannot exist. Write down this simple relation, then we'll do numericals over it. Majority of questions from this chapter comes from this sphere, hollow sphere, solid conducting sphere. Done? Noted up to here?
Yes, sir.
Okay. Let's move on to the question. The type of questions that you get on sphere is you have, let's say, a system of 3 concentric spheres. First sphere have charge q1, second have charge q2, third have charge q3. Radius of the first sphere is, let's say, r1. Radius of the second sphere is r2. Radius of the third sphere is r3. You're supposed to calculate potential at different points. Let's say this is point A, this is point B, and this is point C. You're supposed to calculate potential at all 3 points. So if you want to get potential at A is kq1 by r1. Now, at A, 3 charges will generate potential. For the first charge, q1 is on the surface of the sphere. Or just to elaborate, let's write in this way. First sphere will generate potential, second sphere will generate potential, third sphere will generate potential. For first sphere, the point is at the surface, right? For the second sphere, point A is inside. For the third sphere, point A is also inside. We'll look at point with respect to sphere, not sphere with respect to point. So with respect to sphere 1, point A is on the surface. With respect to sphere 2, point is inside. With respect to sphere 3, point is also inside. Is it clear?
Yes, sir.
Okay, now. So potential at A due to the first sphere is it's kq1 divided by r1. This is at the surface. What is inside? Inside potential is same as that on the surface, means the potential on the surface of second sphere and potential inside the second sphere is same. So I would write this as k q2 by r2. Similarly, for the third sphere, it's k q3 divided by r3. Similarly, if you want to get the value of potential at point B for the first sphere, it's outside. For the second sphere, point B is at the surface. And for the third sphere, it's inside. So we'll say V1, it's outside. For V2, it's on the surface. For V3, it's inside. So VB is outside the sphere, it's KQ1 by R2. V2 is KQ2 by R2 its surface. Because when you go outside, the separation is from center of the sphere to the point. From the center of the first sphere to the point B, the separation is R2. V3, it's KQ3 divided by R3. Is it clear?
Yes, sir.
Similarly,
Yes, sir.
we can calculate potential at C. So at for C, for first sphere, it's outside. So it's KQ1 by R3. Similarly, for second sphere, it's also outside, KQ2 by R3. Why R3? because we need separation from center to the point. And for third sphere, the point is on the surface, so it's KQ3 by R. Is it clear, everyone?
Yes.
Yes, sir.
Okay, note it down. Okay, in class 12, did you take tuition somewhere?
No, sir.
No. So I'll be sending in the homework, I'll be sending some 3 solved examples, and the rest of the questions will be from PYQ. Just 3 solved examples. Huh? Just yes, written.
Yes, sir.
Okay,
Yes,
we'll
sir.
stop. Okay, we'll stop here. I'm sending some homework questions. Then tomorrow, maybe I'll have a class, and tomorrow we'll finish this potential. Let's try to start capacitance. Okay, we'll stop here.